in tutorials, I prefer to introduce some exercise. Now, first, let's look at the chain rule. In some cases, there are some intermediate variables in the function. For example, the function f, it's respect to x, y, z, but they are intermediate variables, and x is the function of u and v, and also y and z. So if we would like to calculate the partial derivatives with u and v, we should first find out the relationship between w and x, and then x to u. So we should do it to all the intermediate variables one by one, and the equations is like that. Now let's move on to the exercise. First, I'll give you these examples. You should calculate dz dt for the following functions. I will give you about 3 to 5 minutes to think about it, and I will give the solution. I think this example is not very difficult. We can just use chain rule to calculate it. And first of all, I will ask a question. Why dz dt here and not partial z partial t? According to the definition, for example, look at this these two equations. They both use partial w partial u, and w is the dependent variables, and uv are independent variables. But in this example, it use dz dt because there is only one independent variable, right? Only if there are more than one independent variables, we use partial w, partial u, or partial w, partial v. But in this case, all the intermediate variables are only related to t, right? So not partial here, right? So according to the definition, we should first calculate all these partial derivatives, right? So let's look at this one. First, we should calculate partial z partial x, and z is equal to this part, and we should calculate partial z partial x equal to this one, right? So the second thing we should do is to calculate dx dt, and x is equal to this part, and so dx dt is equal to this one. Good. Okay. Some students ask, where can I find this PPT? You can find out this PPT in Frankie's website. And for the intermediate variable y, we should also do the same thing, right? We should first calculate partial z partial y, and the equation is like that. Z equal to this one, and we partial z partial y should be like that, right? And dx dt, and y is equal to this part, so dx dt is just like that. Good. And then after we have calculated all these things, we just use chain rule to add them together, and then we will get this thing, right? So in this equation, the final solution is related to x and y, but we would like to calculate the relationship between z and t. So we should replace x and y by t, because x is equal to this one, right? So we can replace both x and y by t. Then it can be written as that. Good. Okay. Then we can also simplify this equation just like that. But this is the first kind of solution to this example. And we also have another way to solve the problem. Because we have known the relationship between z and x, y, and also the relationship between x to t and y to t. So we can first use t to replace x and y in the very beginning, right? So the z should be a function of t. Only t is here, because because both x and y are replaced by t, right? So so now it will be more easily to calculate dz dt, right? Because z is equal to this part, and it's a function of t, and we can calculate dz dt just like that, and we can get the same solution. Good. Any question? Let me check the.
Can you show
check.
the say method, another method again?
I think some students are saying something, but I cannot hear very clearly.
Can you show the another solution again?
Okay, you mean the second solution?
Yes, thank you.
Okay. The first solution we just use chain rule. We use the definition to calculate dz dt. We first find out the relationship between z and both the intermediate variables x and y, and then x to t and y to t, right? So the second solution, our insight is that we just give up x and y. I mean, we would like to give up the intermediate variables in the very beginning. So how can we do that? We can in very beginning we can replace x and y by t, because the relationship between x and t and also y and t are given, right? So maybe I would like to z is equal to z is the function of x and y, and x is the function of t. So x equal to this one. So the x can be replaced by e to t, right? X power 2 can be written by this. Good. And also we can do it to y. Y is equal to this part. So it's like that. These two parts are equal, right? Because we just replace x by t and also y by t, because the relationship has been given. So now the z is the function of t. X and y no longer exist, right? So now we already know the relationship between z and t, and the question and the example asks us to calculate the dz dt. So it will be much more easy. Good. Am I clear? Let me I think there is some students are saying something again, but still not very clear. So can you be louder?
No question.
Okay, good.
But I saw some others asking questions in chat box.
Oh, I'm checking them. But in fact, I'm not really understand what does it mean. How are derivative and partial d related? I think maybe you are asking the first thing I talk about. I ask you why dz dt here, but not partial z partial t here. I'm not sure whether you would like to know this. I will say it again. Because when there are more than one independent variables, for in this example, we have two independent variables, u and v, and no matter how many intermediate variables, we only care about independent variables, because finally we only care about the relationship between dependent variables and independent variables, right? So if there are more than one independent variables, for example, u and v, we should use the partial, right? Because this is because the definition is just like that. But in this case, we have only one independent variable, t, right? So, for example, we only have u, but not v. We can just use d, z, dt to represent it. Good. Am I clear? More questions? Oh, if you have more questions, maybe you can send email to me. Okay. Then we will move on to the mean value theorem. It talks about that if the function of x, y, z be continuous and have continuous first partial derivatives in some domain, then the straight line segment P0 to P, maybe it satisfies this equation. So we will use our example to further introduce it. Again, you can first do it by yourself. Plot it. and so the segment can represented by this one, right? T from 0 to 1, and x, y, z equal to 1 plus t. Good, because the segment is from 1, 1, 1 to 2, 2. Good. And now the question becomes we should calculate t. If the t is decided, then the point will be decided. Good. So we would like to find out the point Q. Q is represented by this. Right. Then we would like to find out which T0 can make the left part and the right part equal. So we can first look at the left part. In this case, it should be F222 minus F111, right? So it's just like that. And use the function, we can calculate it. It should be 9, right? So then we move on to the right part. The right part is something like that, and H should be 1. K and L are also 1, because H is the difference in the x x direction, right? And I will write something to make it clear. In this example, x0 should be 1, right? Y0 should be 1, and Z0 should be also 1, right? And this one should be 2. Also, this 2, and this one 2. So H should be 1, K should be 1, L should be 1, right? So this part is 1 and also 1 and also 1. Good. Then the only thing is to calculate partial f, partial x, and the partial f, partial y, and partial f, and partial z. Right. So it should be 1 times partial f, partial x, partial f, partial x, should be 2 times x, right? And here, x is equal to 1 plus T0. So it should be 2 times 1 plus T0. Right? So we can also do it to partial f, partial y, and also partial f, partial z. In fact, they are all the same. So, and it's equals to this one. Now, according to this equation, we can calculate T0. And after T0 is decided, the point Q, we found out the point Q, right? Should be like that. Good. And the question? Let me check. Okay. You would like to know how the H be calculated? In fact, you should look at this equation from the right to the left. This part equals to the left part. Left part, I mean, okay. And this part represents the right part. So the left part should be, in fact, f x0 plus h and minus f x0 y0 z0, right? And this one should be f222, right? So we calculate it. It should be 4 plus 4 plus 4, right? Should be 12. And f111, this part should be 111, right? So it should be 1 plus 1 plus 1. Should be 3, right? So 12 minus 3 should be 9. Good. Good. Yx equal y equals 0. What does it mean? You mean why the Q can be represented by x equal to 1 plus T0 and also y equal to 1 plus 0? Sorry, 1 plus T0. So they are all equal because the first we should I will simplify it by 2D because the P0 is 111 and P is 222, maybe this point, and the segment is from P0 to P, right? So all the point in this segment should be 1 plus T0, and all the x, y, z should be 1 plus 0, T0, right? Because they are all on this line segment. Good. Yes, position vector 111. Good. Okay. Any more questions? let's move on to the next part about directional first, we should understand the definition of direction. Partial z partial x, we only know the change in the direction of x, and partial z partial y, we only know the change in the direction of y. And if we would like to know the change in arbitrary direction, we should use this one, right? So first of all, we should know what's the definition of direction. Direction should be a vector, and in fact, it's a unit vector. We should divide it by its norm, its length. Good. So first, I will give you some very easy examples to ask you to calculate the direction. Oh, okay. The password for this slide should be Frankie. Okay, now let's look at the solution. And according to the definition, we should first calculate the length of each vector, right? So for the first one, we first calculate the length, and then we divided the original vector by the length and get this one. It's the direction of this vector. And also for the part B, we should also first calculate the length and use this definition to get the direction. And for the other two examples, again, we first calculate the length, and both of them equal to 1, right? The length for this vector should be 1, and also for this vector should be 1. So the original vector should be the direction. Good. I think this exercise is easy. Okay. Now let's move on to the next part. So now we have know the definition of direction. Then, any questions? Yeah. According to the definition, the direction should be unit vector. As its unit vector, so it should be divided by the length. Good. Okay. Now let's move on to the definition of directional derivative. And this equation represents the definition. We should first decide the unit vector of the direction. I mean, if you would like to calculate the directional derivative, you should first know the direction, right? We would like to know the change in this direction. So we should first calculate the direction. I mean the unit vector, right? Then we can calculate the derivative in this direction by this equation. We should also first calculate partial f, partial x, and partial f, partial y. And then we calculate partial f, partial x times u1. U1 is the first part, I mean the top one of the unit vector. And the u2 is the bottom one. I will give you an example to further understand it. Okay, let's look at the solution. First, we should decide the direction, right? Because it's from point P to Q, so the vector should be like that. And in order to decide the direction, we should change it to a unit vector. So the first thing we should calculate the length and then divide the vector by the length and get the direction. Good. And after we get the direction, in fact, we have know the U1 and U2 in the definition of directional derivative. Then the remaining thing is we should calculate partial f, partial x, and partial f, partial y, right? So first we calculate partial f, partial x, and it's very easy, right? So it should be like that. And in fact, for the particular point P, it should be equal to 1, right? So again, we do it for partial f, partial y. And for this point, it should be 2. Good. Then according to the definition, I mean, we should first this one equal to 1 here, and U1 is here. Multiply them together. And also for this part, then we get a solution, right? So let's move on to the next example. Okay, let's look at solution. First of all, again, we should decide the direction. As we all know, according to the definition, the direction should be unit vector. So we should first calculate the length, and the length should be 1, and so this one should be the direction, and then according to the definition of directional derivative, we should calculate the partial f, partial x, and partial f, partial y, and the particular point should be 1, 1, right? So we can calculate the partial derivative, and then we, according to the definition of directional derivative, we can calculate the something like that, 1 times cosine alpha plus 1 times sine alpha. Good. And I think it's not very difficult. Now let's move on to the question B. Now we have known the directional derivative like that. How can we decide the largest or smallest directional derivative? In fact, it's a question about sinusoidal function. We already know the directional derivative is like that. And in order to decide the largest or smallest value, we should first reformulate it as a sine function. And then we can easily decide which alpha will make this one biggest or smallest, right? So when alpha equal to this one, we can get the minimal value. And now the the unit vector should be like that. I mean the direction. And also we can also get the maximal value, 1 alpha equals to pi divided by 4. Good. Okay. As time is limited, I have to be quickly. So now let's move on to the definition of gradients. If f is a function of x and y, I mean two variables, the definition of the gradient should be like that. The top one should be partial f, partial x, and the bottom one should be partial f, partial y. Now, let's move on to the exercise. Okay, let's look at solution. According to the definition, we should first calculate partial f, partial x, and partial f, partial y, right? So the partial f, partial x should be like that, and also the partial f, partial y. Then the gradient should be like that, according to the definition, right? Now let's move on to the next example. Okay. Again, we should first calculate partial f, partial x, and partial f, partial y, and then we can write down the gradient according to the definition, right? Then let's move on to the theorem. If we know that a function, if a function equals to a constant, it represents a surface. So the physical meaning of gradient should be the normal vector of the surface if the gradient is not zero. Now let's look at this example. You can find the PPT in Frankie's website and with the password Frankie. As there are so many students in this class, so I'm so sorry that I cannot answer all the questions. So if you have further questions, you can email us after class. Thanks. Now let's look at this example. And in order to decide the tangent plan, we should first know which is the normal vector, right? So according to this one, I just introduced, the normal vector should be the gradient if it's not a zero vector, right? So we should first calculate partial, if this is a u function, partial u, partial x, and partial u, partial y, partial u, partial z, then we get the gradient according to the definition. And in this point, there is a typo here. The point should be 3 to 1, and we can get the gradient like that. And it is not the zero vector, so it's the normal vector of this plan. So we can easily get the tangent plan just like that, as the normal vector have been found out. So now let's move on to the next example, and a very similar question. First, we should decide which plan it is, and so we should rewrite this equation. We rewrite it like that. Equal to 0. And if we define it as a u function, then its function equals to a constant, then we can easily find its plan, right? So again, we will calculate the gradient. So the gradient is like that. And again, it's not a zero vector. So the gradient should be the normal vector. In this point, the particular vector should be like that. In fact, there is a minus here. Then we can also decide the tangent plane, right? Now, let's move on to the last part in this tutorial. We will talk about the divergence of a vector field. First, let's introduce the definition. The definition should be like that. It's a dot product. And let's move on to the example. In fact, the F is a vector. So let's calculate the divergence according to the definition. Okay. So for this vector field, the P should be this part, and this part is Q, and this part is R. Then we can calculate the divergence according to the definition. Then we calculate the partial P, partial X, it should be 2 times xy, and partial q, partial y, it should be xz, and partial r, partial z, it should be 0, right? Because there is no z in this part. X, y are considered as a constant. Good. Then let's move on to the next example. Okay, let's look at this example. And again, this one is P, and this part is Q, and this one is R. Then according to the definition, we calculate partial P, partial X, partial Q, partial Y, and partial R, partial Z. So we get the solution. Now let's move on to the last example in today's tutorial. Oh, OK， 好。OK, let's look at the last example. So the first question asks us to calculate the gradient, and so according to the definition, we should first calculate partial partial x should be 2x, and partial f, partial y, 2y, and partial f, partial z, 2z. So in fact, we can also write the vector in this form. So we can also write it as 2R. So it's the gradient. And for the divergence, according to the definition, the P is equal to X and the Q is equal to Y and Z is equal to R, right? So we can get the divergence according to the definition. Okay, so now let's, it's all of the contents of the tutorial today. And I'm very sorry that I have to go aboard now. So the tutorial have to at the end. So if you have further questions, please email us. And thanks for everyone coming today. Okay. Bye-bye.